If anyone's online, could you mute, please, because we can hear the typings. Renuka's an expert in hunting for dark things in galaxies, but not so much dark matter, more black holes and the influence they have on the stars around them. And we'll hear about some of this work today. Renuka is currently a postdoc in Liverpool working with Sebastian Canan. We got in contact recently because there's lots of exciting news data for the Omega Centauri globule cluster that we're going to be talking about today and tomorrow. So if any of you have interests in intermediate mass black holes, galactic nuclei, globular clusters, dynamics, mass modeling, and just data and stuff, please do try and track Renuka down today or tomorrow. Ping me if you want to know a schedule. And otherwise, over to you.
Thanks, Justin. Hello, everyone. I'm Renuka Pechetti, and I'm currently in my third year postdoc at Liverpool John Moores University, working with Sebastian. So I don't know how many of you are familiar with IMBHs or work on that, but I'm going to give a little introduction about that and the work that I did relating to these exciting objects. So before going into IMBHs, I want to talk about stripped galaxies. Usually we have interacting galaxies everywhere in the universe. How these are formed are they interact with each other and get disrupted. The gas goes away, the stars go away, and what we are left with is sometimes these remnants of galaxies, which are also called as ultra-compact dwarf galaxies, termed as UCDs in short. And a lot of exciting things can be found in these UCDs because they have been galaxies in the past. So you can probably find a massive black hole inside these UCDs. And these have been proven by recent discoveries, such as from Anil's work or Chris Ahn, Karina Vogel. They found many of these ultra-compact dwarf black holes in them. And this plot here shows the mass of black hole versus the mass of UCDs. And this was a relation that was predicted by Stefan Miesky, 2013. Where all these objects contain pretty high mass to light ratios in them. And the highest mass to light ratios were detected to have a 10% black hole in them, which is quite massive for a very tiny object with a very small effective radius. And if we see that, like, these high mass galaxies, which are around 10 to the 9 solar masses, galaxies also might contain, used to have black holes. The lower mass galaxies also might contain black holes in them. And if these lower mass galaxies were stripped apart by some bigger galaxy, we would find them in today's globular clusters, or which coincide with the globular clusters. And they will be a stripped nuclei, a very low mass stripped nuclei. So we want to hunt for these low mass end here galaxies, clusters, which are usually residing inside like Milky Way like galaxies. And we want to find objects that are lurking inside the center of these clusters. So why are these IMBHs important? Because they also connect, when we find these kind of intermediate mass black holes, or like black holes in these objects, which are usually from the mass range of 100 solar mass to 10 to the 5 solar masses. There are different black hole formation scenarios, which show that black hole can be seeded like 10 to the 4 solar masses in the early stages of the universe formation, where these halos were seeded by very heavy black holes, and then they merged and accreted and formed supermassive black holes for today. And then there's another formation scenario where smaller black holes were seeded in the halos, and then they merged and grew together to form supermassive black holes that we see today. And if we manage to find like these direct collapse black holes, which were seeded earlier, and they would still be existing in current day universe. And when we manage to find them, we can probably prove that, okay, this formation scenario also exists for our black hole seed formation. So how to find these strip nuclei and black holes? Several methods exist for detecting black holes. One is accretion based, where the black hole is active and it's accreting around, and we can see the signature in the emission lines that are formed in like AGN. The lowest, a lot of low mass black holes have been detected. The lowest one detected was around 50,000 solar masses from this paper by Vivian. And then we also have X-ray and radio detections. Like the most robust example that we have for a black hole, an IMBH, is the HLX1, which is around 10 to the 4 solar masses. And we want to find like these type of detections, but these are quite rare because most of the black holes of this size won't be accreting heavily for us to find these robust detections. Another method is tidal disruption events, which is nothing but when a star comes close to a black hole, it gets ripped apart. Half of the star gets ripped apart, and it creates a flare. And based on the peak luminosity of this flare, you can actually tell whether you can tell the mass of the black hole. Like, for example, in this paper by Sebastian Gomez, he finds a couple of objects where the black hole disrupts a white dwarf, and that can only be done by an IMBH, not anything greater than 10 to the 5 solar masses. So this is actually a pretty good way to find black holes now, because a lot of transient surveys are going on, and I think the future of IMBHs is definitely TDEs. And yes?
You say that there's only this mass range that can do the tidal disruption events. Why is that?
I mean, like for an IMBH or like for a white dwarf, to create a white dwarf flare, you can also get it's the black hole mass has to be below 10 to the 5 solar masses. For like what happens is like suppose it's a very high mass black hole, the disruption of the star falls inside the event horizon, so you cannot detect it. And then finally, this is the one that I use, is using stellar dynamics, which is using infrared data. I usually use IFU data, which is integrated field kinematics, which I'll be talking more about. And so for IMBHs, for supermassive black holes, the best place to look is obviously like high mass galaxies greater than 10 to the 9 solar masses. But for IMBHs, dwarf galaxies are less massive, and are best places for to look for these black holes. And to get the best kinematics, we target like the most massive clusters in nearby galaxies, because for the strip nuclei, today's strip nuclei would look like globular clusters for us, and we have to target those to get any kind of IMBHs if they might be residing in it. For example, in Milky Way, we have Omega Cen, which is the most massive cluster and been studied most detailedly. And then we have another galaxy, our neighboring galaxy, Andromeda, and we can study like the most massive clusters in them as well. So first, I'm going to talk about the M31 cluster, which is that, because for the for Milky Way type of galaxies, we usually use the motions of stars around the black hole, which requires really high resolution data for individual stellar velocities. But for galaxies that are further away, we use integrated field kinematics, which look like that, where nothing but, for people who are not familiar with IFU data, it is each pixel there contains a velocity dispersion of stars. Like it's a collective motion of the stars, which gives a dispersion in that bin, and the mean is the velocity of that bin. So we use since we cannot resolve individual stars for galaxies that are further away, we use that kind of data. And for Milky Way, I use individual stellar velocities. So we chose the most massive cluster in BO2 in the Andromeda, which is actually termed that. It used to be G1, which was considered the most massive cluster, but it's not anymore. We had this beautiful HST data from 2 different filters that we use. And we found that it was the most luminous cluster as well. And then we got the kinematic data, which is from Gemini NIFs, pretty high resolution. And as you can see, this is the velocity map, and you can see that it's pretty strongly rotating. And for a globular cluster, it's not that common that it's that strongly rotating. And then it also has this velocity dispersion map, or the VRMS map here, I think, which shows like there's a peak in the dispersion right at the center, which is kind of a positive sign, because if there was a heavy dark object sitting right at the center, the motion of the stars would be pretty high at right at the center. So for my dynamical modeling, I need 2 different data sets. One is the optical data, and the other one is the kinematics. The optical data is for creating luminosity models or mass models. So here is the surface brightness profile of the cluster here, which I used a King and a Sersig profile. Usually globular clusters are defined by a single component profile. But here we actually divided it into 2 component profile, which made us suspect that it is actually not a globular cluster. And we use this light profiles or mass models to disintegrate them into multi-Gaussian expansion models, which is nothing but you convert these light profiles into multiple Gaussians of different radii, so that they are inputted into our dynamical models. And then we use Jeans anisotropic modeling to estimate our black hole mass, which is what essentially it does is you take the light profile that I described to you earlier, and you estimate what would be the line of sight velocities from that light that we are seeing. And you compare that line of sight velocities with the kinematic data that or your observations. And if there is a difference in these observations and the estimated line of sight velocities, it would appear as some kind of dark mass sitting at the center, because the light will only is coming from the stars, but you cannot detect anything that is coming from the black hole. So that excess mass would be given to the IMBH in this case. And our models actually have 4 parameters, which is the mass to light ratio, black hole mass, anisotropy, and inclination for the cluster. So based on, we ran an MCMC analysis on the genes models, and we estimated that the black hole mass was around 10 to the 100,000 solar masses in this case. And as you can see, it is degenerate with the mass to light ratio, which is nothing but a scaling factor to match the observed line of sight velocities that were predicted from the surface brightness profiles. And then there's this anisotropy parameter, which actually shows that it's not that much anisotropic, because the cluster is mostly spherical. And we find the anisotropy close to 0.15 here. The inclination, again, we cannot determine it perfectly because it's spherical, and it does not actually have that much effect on our models. And this was 3 sigma detection for us. So to just visualize it better, here is the velocity dispersion profile in 1D. This is the VRMS, which is just the square root of rotation velocity and plus the dispersion of the cluster. And as you can see, this is the no black hole model, which actually just says that if you do not include the black hole in the model, what would be the estimated dispersion? And it's way off what we get from our observations here in the red. So what are the possible alternatives to an IMBH? Even though we predict an IMBH, what happens is that it is always the most contentious thing about an IMBH is that it can also be considered as a collection of stellar mass black holes. To remove that, it is quite hard because they kind of mimic each other. So as I was describing earlier, for my multi-Gaussian expansion models, I assume an IMBH with a very small radius and which is a Gaussian. But if you replace that IMBH with probably some kind of dark mass which has an extended radius, and some mass, you can assume that it's probably a collection of stellar mass black holes. So I did that, assuming a Plummer profile, and assumed that it is a central dark mass with some kind of radius. And I gave that as an input to my dynamical models instead of an IMBH. And I actually found that the best fit models actually show that it's quite unresolved at the center. But I still have an upper limit of around 0.6 parsecs, which is resolvable in my data set, which does not completely rule out an stellar mass black hole scenario. But that's just the upper limit. But we have additional evidence saying that that favors an IMBH scenario, which is it being a strip nucleus. So the first evidence, as I was talking about earlier, it has a 2-component profile, which is unusual for a globular cluster. And then we also have, we found the metallicity gradient in this of around 0.2 dex, right within 1 arc seconds, which is around 3 parsecs. And this is quite similar to even omega sen, where it has a metallicity gradient. And then we also had, we have a pretty strong rotation, which is unlikely for a globular cluster, which has a V over sigma of 0.8, where V is the velocity, sigma dispersion. And for a strip nucleus, usually these components are higher, but for a globular cluster, the V over sigma is usually around 0.3. So if it's a strip nucleus, the inference here would be, it used to be a galaxy and that would contain a black hole in it. And our main thing would point that it is an IMBH and probably not a collection of stellar mass black holes. So this is for the Andromeda cluster. And here I have the cluster mass and the black hole mass relationship. It is one of the most common relationship that usually people who study black holes plot. So these are the black holes, probable black holes in systems like GZs or globular clusters. And these are here the UCDs that I was talking in my first slide. They have pretty high black hole mass percentage in them. And these are the objects that have both nucleus star cluster, which is nothing but a very dense cluster, and also containing a black hole. But the main thing you have to note here is just that my object and the most massive cluster in Andromeda falls on this 1% cluster mass, which is probably supposed to be. And it falls perfectly on the relationship. And now I'm going to talk about omega sen, because that was the most massive cluster in Andromeda. And now I can focus on Milky Way's most massive cluster, which is omega sen. And this has been studied a lot, like more than 2 decades. and is suspected to contain an IMBH, which is still not proven. But I think we are getting close, because now a ton of data is coming out soon, which I'm also proud of to be a part of. But I'm going to talk about some preliminary results that I have. So the most contentious thing that was focused on was finding the center of omega sen, because actually it's a very delicate thing. This omega sen is really big. It has a core radius of maybe around 5 parsecs. And finding the center is really complicated because it's pretty flat. And so these are 3 different centers that exist in the literature on that I compared my data with them. And they estimate this paper from Noyola 2010 paper estimates a black hole of around 4.7 times 10 to the 4 solar mass, whereas this paper, which is Anderson and Van der Marel's 2010 paper, does not actually predict a black hole because of the center differences. So this is really crucial to find a good center. And I'm going to try and explain how I estimate the center for this. So we have this amazing data set from Muse for omega sen, which covers approximately the half-light radius. And this was observed right at these 3 different centers. We got the highest possible resolution data using the narrow field mode of Muse, which has a resolution of around 50 milliarc seconds. Using this data set, I'm trying to figure out like what is actually happening right at the center of this cluster. And we are pretty complete within the, like at least 50% complete around 20th magnitude. And we have really high quality data. As you can see, this is the HST catalog that we have in the blue. And this is the narrow field mode data within the 20 arc seconds, which is around 5.5 parsecs for omega sen. And the WFM is the wide field mode data, which is a little lower resolution than the narrow field mode data, but covers a wider range because it has a bigger field of view. And probably. So we did a k nearest neighbor analysis on this data set. What we get is actually, so this is the inner 20 arc seconds of this cluster. And as you can see, this has a rotating core, which is actually opposite to the global rotation, which you will see in the next slide. But what I want to show here is that this is the center that was predicted in Noyola 2008 paper. And this is the Noyola 2010 paper, which was based on the kinematics of the cluster. And this center was predicted based on the number density counts of just the photometry of the cluster. And these 2 crosses represent the 2 different centers that I find based on this rotation and the dispersion. This is the dispersion map, and this is the rotation map. And as you can see, these 2 centers are quite off-centered. It's about 8 arc seconds away, and not usually found in any of, obviously, not any of the clusters have it in general. And as you can see here, this is just a lowest smooth map of the cluster, and this is the global rotation of the cluster, and this is the inner 20 arc seconds that I was showing you earlier, and it is actually counter-rotating. And this is quite new and also found in one of the clusters like M15, where the inner 10 arc seconds or so was actually off-centered with respect to the outer rotation. And this is quite interesting because this is the first time this has been found. And due to the high resolution data that we have within this 20 arc seconds, it is all the narrow field mode data that we have. And then I perform kinemametry on this lowest maps, which is nothing but I'm trying to find the center of this cluster. As you can see, sorry, how do I go back? Yeah. As you can see that it's quite degenerate in this area. Like you can have centers here or along this axis. In my trial attempts that I did, I found that the center was almost lying along this rotation axis. And I did kinemametric analysis on it, where it actually tries to fit ellipses. It assumes that an ellipse rotates in using a cosine law, and it does Fourier transforms on these ellipses and minimizes the coefficients of the ellipses, the best fitting ellipses. And in those coefficients, here is one of the coefficients, which is K1, which determines the changes in rotation of the cluster. Like if there's a peak here, it shows that, okay, there's a rotation right there. And then this is the global rotation of the cluster. And then this is the K5 term, which actually shows that K5 is nothing but it shows deviations from the original main rotation. So it has to be approximately 0, but it kind of peaks, which shows that, okay, there's a counter rotation at the center. It's also visible in the position angle of the rotation, where it's obviously counter rotating with respect to the rest of the cluster. And then here is the rotation profile that I did based on maximum likelihood approach. I just binned the data, and for each bin, I predict a velocity based on the line of sight velocities that I get. And each bin has at least 100 stars in it. And as you can see, this is actually typical Grobler cluster rotation profile, but there is also this peak, which indicates a counter rotation, and which is also seen in this position angle map, where this is rotating in like southeast direction, but this is around like obviously opposite to that, opposite to the counter rotation. So in all of this, I try to figure out how much it is rotating. It's around like 4 to 5 kilometers per second, counter rotating near the center. And then I compare it with different centers that I'm getting. And the most, the closest that I find is the VDMA 10 paper, which is the Vander Marel and Anderson 10 center that they estimate, where they actually find this, where I find that it's counter rotating in the when I use their center, but in the other centers, I actually do not find that. And this definitely would make a difference in estimating the black hole mass, which when I run it through the dynamical models. And here are the velocity dispersion profiles. So this is interesting because so the Noyola 2010 paper, they estimate the center based on the dispersion profile, and it kind of peaks towards the center, which kind of indicates a black hole. There might be an IMBH in it, and they estimate an IMBH of around 50,000 solar masses, whereas these guys do not. So here I'm comparing my news data with their observations, and I find that actually the profiles look quite similar when I use their centers, and all I have to do is now input these velocity dispersions into my dynamical code and get a black hole mass estimate from this. But when I compare my data with different centers, like here I have the kinematic center based on the rotation or the counter rotation that I find. With the other center profiles, I find that they are actually within 1 sigma of each other. So there might be a large scatter right near the center where probably the profile is much flatter than it was estimated in this paper with a black hole in it. And apart from the dispersion profiles, there was a prediction by this paper, Baumgart 2019, which says that if there was indeed an IMBH at the center of this cluster, we would have a tail of these high velocity stars. This was actually a prediction from the simulations that were run by Hoger, Baumgart. And I try to find like if I actually can see this tail in my data set. And this tail is to be observed within the 20 arc seconds of the cluster. And what I find is actually this is all the stars, but their prediction was based on the stars within the 20 arc seconds. And I don't find a lot of stars that are higher than or like a tail of high velocity stars. It's supposed to be around 20 stars, but I find like around 1 or 2 stars that are pretty high velocities. But they need more observations to confirm that they're actually really high velocities. And for now, I do not find any high velocity stars. And it can say that maybe the black hole mass is low, or it might need different kind of simulations for different size of black hole, because they did simulation based on a 50,000 solar mass. But I might need some simulations for a lower mass IMBH. So for now, there is no evidence of an IMBH based on just this data, but it cannot be ruled out completely as well. Oh, and sorry, and there is going to be soon a HST proper motion catalog that our group is doing, which can probably show some more stars, because all these are just line of sight velocities, and they might not contain really high velocity stars, but the proper motions can still be high velocities close to the center. And to get the dynamical models or a black hole estimate for the omega sen, we again use the same method that I did for BO23G78 in Andromeda, which is getting a light profile. And here you can see these are the multiple Gaussians that I use. This light profile was created using HST catalog from Bellini 2017 and Gaia densities from this paper. I think this is 2018, sorry. And we combine it and get the multi-Gaussian expansion models for this. And we do some discrete genes models now. Earlier it was IFU database, but now we use individual line of sight velocities. Here I am assuming a constant mass to light ratio and just a simple IMBH. And based on my center, I get a black hole mass of in between 10 to the 4 to 10 to the 5 solar masses. But these are just preliminary models, and we see that the fits are actually not that great for a constant mass to light ratio. So we try to include a varying mass to light ratio, where you assume a mass to light ratio for each Gaussian component that I'm actually including in the models. And instead of a simple IMBH, I also try to assume a plumber profile, which I was talking about earlier. For the other object that I was talking about, where I add a plumber profile right at the center with an extended radius, and try to get a black hole mass estimate using this, and to check whether if it's a resolved or an unresolved source. And for my preliminary, again, models, I'm using a varying mass to light ratio profile. I do get a black hole mass, which is unresolved, but there's still some things that need to be tweaked. But from what I have run the models for this center, I'm getting pretty unresolved profile. Sorry, unresolved IMBH, but I have to run it for different other centers as well and check if it matches the literature too. And so this is omega sen, and We have, again, strong evidence for a stripped nucleus for omega-sen as well, because of its significant metallicity spread. As you can see here, it varies of around 1.2 dex, has multiple stellar populations, which is pretty strong evidence that it is not a globular cluster. And several studies actually recently have shown that Omega Centauri is actually a former nuclear star cluster of the Gaia Enceladus or Sausage Galaxy, based on all the Gaia data that was published. These papers have suggested that it is a strip nucleus. And again, so it makes it a really strong candidate for hosting an IMBH instead of maybe stellar mass black holes, which I believe to be true. And then on the black hole cluster mass relation that I was showing you earlier, this is my object, and this is omega-sen right here, which again falls in this relationship perfectly. And I have got recently more data from other clusters in Andromeda, which is again Gemini NIPS data. And as you can see here, this is the velocity dispersion maps, and these two are really strongly rotating. This is G1, which is quite famous, and said that and is expected to host a black hole in it from other paper. And this is a cluster which has not been studied yet, but we have a really strong dispersion profile for this as well. As you can see in these maps, for G1, actually, surprisingly, we have a really flat dispersion profile, which might indicate that it might not host a black hole. And it is actually a really interesting result because it has already published black hole mass. And I still haven't run dynamical models on this, but yeah, it will be out soon. And for this, it actually resembles the object in that I studied in Andromeda, the most massive cluster, and is expected to host probably some kind of IMBH in it, since it also has a peak in the dispersion profile in it. And I'm hoping to get these published soon after I finish my dynamical models on these clusters. So just I'll leave you the summary. It's just detection of IMBHs in both these massive clusters. Yeah.